Hey guys, welcome back. Day 13, Electron Configuration 1. We're going to get started with electron configuration, and if we remember, it's N, L, and then the number of electrons. So N was the energy level, L is our orbital shape, and obviously the electrons are the electrons in the orbital. So we talked about L 0, 1, 2, 3. If L is 0, that is an s orbital. 1 is a p, 2 is a d, 3 is an f. So let's go into how we do this. We've already did elements 1 through 10, and so now we're in number 11. So sodium's number 11, right? 11 protons. 11 electrons. Should have 11 electrons. Now, its core electron count would be 1s2, 2s2, 2p6, right? That happens to be neon. And then we go to 3s1, 1 electron. There we go. Right? There's 1 electron in 3s. Right? So make sure you have your periodic table out. So you can see sodium. Sodium is in period 3, group 1. Group 1, period 3. And the alkali metals there. Alright, and so we have our core electrons in green, noble gas core, and our valence electrons outside. In fact, we have 1 valence and 10 core. So that works out. So neon has 10 electrons, so we have a total of 11 electrons. It works out great. So I believe we're going to use boxes here. 3s. Right, for our orbital notation, we have 1 electron in 3s. Right, 3s1. The first one, by convention, we're up. So it's up arrow by convention. Alright, so for this electron, what is N? N will be 3. What orbital are we in? S. So that means L is 0. Remember, M sub L is negative L through 0 to positive L. Well, if L is 0, M sub L can only be 0, right? There's only one orientation for an s orbital. And since we're up, we're plus 1/2. And that's the quantum numbers for that last electron. Now, each of the other 10 electrons has quantum numbers. We're just doing the last one. Magnesium, its core is still the noble gas in the period above, which is neon. And then we have 3s, and there's 2 electrons now. 3s, up, down. So this electron, N is still 3, L is still 0, M sub L is still 0, MS is different, minus 1/2. So this has to go with the electron spin, doubling the number of electrons per orbital. That's all that we did there. Alright, so it's the same electrons. Now, this electron, alright, that electron in green here, has the same quantum numbers as sodium's electron, because it's the same electron. It's going to have the same electron configuration numbers, alright, or electron quantum numbers. You know, think of each atom as an empty stadium with the seats, and each quantum number is the ticket. Right? So it's section 3, rows, level 3, section 0, row seat 0, minus 1/2. Right? It's just the tickets. All right? Think of it. You can think of it that way. All right? Aluminum. Noble gas core still neon. And then it's 3s2, and then We skip over to 3. It's a P, and it's a 1. Right? And it gives us 13 electrons. 3s. Now there are 3 boxes for 3p. How do I know that? Again, so how do we know that? Well, right, the number of orbitals, right, would be, well, the number of electrons is 2l plus 1, right? No, number of orbitals, excuse me. Number of orbitals is 2l plus 1. Right, so if L is p orbital, p is 1, it's 3 orbitals. Also, though, just look at the periodic table. You know, the S block has 2 electrons, and it's 1 orbital, right? The P block has 6 atoms, 6 electrons, 3 orbitals. D will have 10 electrons, 5 orbitals. F will have 14 electrons, 7 orbitals. So it's just half the number of elements as well. All right? So, and again, you guys will do this enough that we'll understand it. Okay, so let's use orange this time. Up, down, up. For this electron, N is 3. L is, well, it's a p orbital, so L is 1. M sub L. M sub L. So M sub L, 0 for that one, goes -1, 0, 1. Now there's more to the story, obviously, but that's where we leave it in Chem 1. So M sub L is going to be -1 because we're in the first box. And then MS will be, since it's up, it's plus 1/2. Let's try phosphorus. Now, before I go into phosphorus, just remember, at any time in these videos, you can pause, rewind, watch again. Electron configuration for phosphorus. So the noble gas we'll use is neon. Then, of course, we're still in period 3. 3, we're in S, and we have 2 electrons, 3s2. 3p, it's p orbital now, and we have 3 electrons in that p orbital. Orbital notation, 3s and 3p. We have up, down, 1, 2, 3. This last electron. What is N for that last electron? It would be 3. L, p orbital, L is 1. M sub L, it goes -1, 0, 1, so it's 1. And MS is up, so it's plus 1/2. Skipping over to chlorine. Still using neon. And then we have 3s2, 3p5. 3s2, 3p5. All right, so 3s. Nope, erase that. 3s, 3p. We have up, down, and then up 1, 2, 3, down 4, down 5. This guy. Now, we can probably guess it's going to be very similar to the last electron in phosphorus because it's the same orbital. N is 3, p orbital, L is 1, it's in the middle, 0 for M sub L, and then, but we're down -1/2. So that's the only difference, is the electron spin. It's the same orbital, so it's going to have the same 3 quantum numbers. Argon. Now, just so we know, we cannot use argon to define argon. Not allowed. All right, because it's not core. Even though it's very stable, it's not core. It's still neon as the core. All right, still neon. Then it's 3s2, 3p6. So we have up, down, 1, 2, 3, 4, 5, 6. That last one right there. So what's N? Well, it's 3. L, p orbital, 1. M sub L, negative 101 is positive 1. MS is down, so minus 1/2. And that's it. That's all we're doing with electron configuration. Alright. Okay, so we do this a lot, and you'll be able to reference this a lot. Okay, so it's not like you're going to make a lot of money because you know the electron configuration, but I'm trying to show you guys the pattern. Calcium. Now calcium is in the fourth period, so we can use argon as my core. And that goes then to 4s2. So in 4s here, we have 2 electrons, up, down. We're going to use this last one here. So what is N? N is 4. S orbital, L is 0. M sub L is 0. MS, we're down, so we're minus 1/2. Titanium. So this is where we have the first issue with d orbitals. Alright, so we got argon, 4s2, and then it's 3d2. That's just how it works out, right? I'm pretty sure that Schrodinger and Bohr and Pauling and all these guys weren't back there 100 years ago saying, you know what, let's just make this confusing for future chemistry students. That's not what they did, right? This is the solutions to the math problem. The d orbitals are off by 1. So we have 3d2. So I'll do the 4s as well, just for fun. 4s, 3d, 1, 2, 3, 4. So 5. 5 orbitals for d. 10 electrons, 5 orbitals. And let's see what we got here. Up, down, and then up, up. This guy right here. Well, what is N for that guy right there? Well, we're in 3, so there we go. L, 2, d orbital. M sub L goes negative 2, negative 1, 0, 1, 2. So we're in negative 1. And we're up plus 1/2. And those are your quantum numbers. Cobalt. Alright, cobalt. Skipping over to cobalt. Argon. And then we have 4s2, 3d. You count them over. 1, 2, 3, 4, 5, 6, 7. Right, just count them over. 4s. Now, technically, the d's are not valence, but we're doing them anyway. 3d. 1, 2. There we go. Up 1, up 2, up 3, up 4, up 5, down 6, down 7. So you notice, and this is why we picked this one, this orbital is the same as this orbital for titanium. It's the same d orbital. So N, still 3. L is still 2. M sub L is still negative 1. Same orbital. But now the difference is minus 1/2 for the spin. Alright, a couple more. We got bromine. Bromine would be, noble gas-wise, still argon. Alright. And we got 4s2, 3d10, 4p5. Right, that's bromine. So 4s, now technically, and 4p. The d's are technically not valence, right? We just did them so I can show you the quantum numbers. Alright, so 5 and 4p, up, down, and then 1, 2, 3, 4, 5. There we go. This guy. So N is 4. L, p orbital, 1. Negative 1, 0, 1. So M sub L is 0. And MS would be minus 1/2. Yttrium. Now we're below. We're in period 5. So Krypton can be my noble gas. And that's 5s2, 4d1. So we'll do the quantum numbers of that d orbital for us. 5s. 1, 2, 3, 4, 4d. We got up, down, and then up. Of course, we're going to do that guy. So N, 4. L, d orbital, 2. M sub L, negative L, the positive L, negative 2, negative 1, 0, 1, 2, negative 2, and then we're up, so it's plus 1/2. First one's always plus 1/2. Indium, skipping all the way over to indium, still Krypton. So we use Krypton here. And then we have 5s2, 4d10, 5p, looks like 1. 5p1. So 5s, that looks like ss. Let's go with 5s, 5p. Up, down, up. Alright, so N for this guy, N is 5, L is p orbital, so it's 1. First p orbital, so it's negative 1, and then it's up, so it's plus 1/2. There we go. Alright, so some more. We got some more to do, and then we'll, alright, so we can do all these. Xenon. Xenon. Can I use Xenon for Xenon? No. I still have to use Krypton. And then we have, it looks like 5, right? 1, 2, 3, 4, 5. 5s. 2, 4d10. 5p, 6. How about that? So there's my 5s. We'll skip the 4ds. They are not valence. 5p, and we got 6. Up, down. 1, 2, 3, 4, 5, 6. So this one right here. L. I'm sorry, N. N is 5. L is p orbital, 1. M sub L, 1. It's the last orbital, so it's negative 1, 0, 1. And MS would be minus 1/2 because we're down. Alright, tungsten. What noble gas can we use for tungsten? Well, tungsten's actually in the 6th period, so we can use xenon. And then, oh, actually, it's big. Xenon. And then we have 6s2, 5d4. And we'll put that 6s2, 5d4 up here. Even though the d's aren't valence. 5d, and we have 4 in there. So, up, down, up, 2, 3, 4. And this guy. So, N, 5. L, d orbital 2, M sub L, negative 2, negative 1, 0, 1, 2, it's 1, and then plus 1/2. And that looks great. Except, it's not. There is an error here. This is not fully correct. And you might ask why. Well, xenon has how many electrons? 54. So if xenon has 54 electrons, 54 and 2 would be 56, and 4 more would be 60. The problem is tungsten has 74 electrons. So 60 and 74 do not equal each other, obviously. So we are missing what? We are actually missing the 4f14. So if we look, tungsten is right here, highlighted. Okay, it goes 6s1, 6s2, boom. Now, technically speaking, lanthanum is 5d1, but there's debate about this. All right, okay, it's debatable. I'm going to give you only, I would ever ask you only ones that are really not debated. So lanthanum is technically 5D1, and then cerium is 4F. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Then back to 5D2, 5D3, 5D4. So technically speaking, we have 4F14 in this, and we need that to get to the 74. Now, a lot of times you'll see this written as Xenon, and it'll be written this way: 4F14, 5D4, 6S2, and we call that the stripping order. And we call it the stripping order is because that's how the electrons are removed. Okay, so they don't actually go on the same way they come off, right? I don't know, maybe my tennis shoes are the exact same way. They don't necessarily, if they're tied, a lot of times I can force the shoe off. If they're tied, though, it's very hard for me to get that shoe on. Alright, that's just a simple example. So these electrons, the S comes off first. Really, P's come off first, then S's, then D's, then F's, depending. Alright? Okay, so technically speaking, when we get down into period 6 and 7, we got to remember the F block. Alright, so that we don't forget these, right? We got to forget these. Okay? These are the ones we can't forget. So that's, even though it's in 6, it's 4F and then 5F. Okay, so let's do another one here. Cerium. Where is cerium at? So let's go back to it's this guy right here. Okay. Alright, and it shows you, by the way, this is its electrons. 2, 8, 18, 19, 9, 2. Okay. Which 19 is kind of fun because it's more, usually it's fun. But if you just actually have the whole, this one may not. It has energy levels, but it doesn't necessarily say what we got here. Alright, so going back here, I can still use Xenon, and then we are in 6S2, 5D1, 4F1. That's technically what I want. Okay. Alright, again, as you can saw back from this periodic table, this is actually 15 elements long. Okay, they're 15 elements long. Okay, so it's just the way it works. There's debate because of whether if this is more a D1 or if F14. There's just debate on it. So don't worry about that debate. Just worry about following the way we're going to show you. Okay. So we'll just do the 4 F's for the quantum numbers. And there's only one in 4F. So N would be 4, L would be 3, M sub L negative 3, and M sub S would be up. And so that would be the quantum numbers for that electron. Okay, Gedolium. We got Gedolium. Where's Gedolium at? Right there. Number 64. Okay, number 64. And so what do we have here? I still have Xenon. 6S2, 5D1, 4F7. Right, 4F7. So if I do the 4F again, 4F box, we would have 1, 2, 3, 4, 5, 6, 7. This one. So N still 4, L is still 3. Now we're in positive 3. You could go from negative L to positive L, and then we're still up. So there we go. Alright, Rutherfordium. Where's that one at? Right there. 104. Alright, so we're going to go 7. Alright, you can use radon as my noble gas. 7S2. Then this becomes 5F14, and then the D1, 2. It's D2. Alright, so let's look at that. Radon. 7S2. Right? And then if I want to do 6D2, 5F14. Or you can do it where you 5F14s first, then the 6D2, then the 7S2. The order does not bother me at all. Okay? But that's where we're at. Okay? Alright, and so just 6D. If we do 6D, 2 electrons, up, down. This guy, N is, of course, 6, because we're in 6. L is 2, d orbital. -2, -1, 0, 1, 2. So it's -1, and we're positive. That's it. That's it. Alright, so if you want to look at nickel here, go ahead and try, pause me, try nickel, and come back. See if you can get it. So nickel, what noble gas can I use? Well, nickel's a first row transition metal, so I'm going to use argon. And then we have 4s2 3d8. And if we use d8 and we use those d's, d8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. This one right here. N. Well, we are in 3, so N is 3. D orbital, 2, -1, 0, 1. I'm sorry. Let's try with D orbital. -2, -1, 0. Alright, and then we're down, so -1/2. Lead. Noble gas for lead. Lead would be way down there, and so lead would be xenon. Alright, xenon, and then we have 6s2. Well, I'm going to actually write it this way. (6s2) 5d10 4f14 6p2, right? 6s 6p. Up, down, up, down. Oops, excuse me. Up, up. There we go. And this last electron, N is 6, L is 1, M sub L 0, and +1/2. Now, in the stripping order, if we were to do this in the stripping order, I have xenon, 4f14, 5d10, 6s2, 6p2. So if we look at lead, and we know what we know about electron configuration, we've learned that full and half, well, we haven't learned about half-full orbitals yet, but full orbitals are particularly stable. All right, that's why the noble gases were stable, if you remember that video. So 4f14 is going to be stable, and 5d10, full Ds, are going to be stable. All right, 6s's are somewhat stable, not as stable as other ones, but it's more stable. 6s2 or S2 is more stable, definitely more stable than S1. And P2 is definitely not stable. So lead can be lead metal, 0, and it's somewhat stable. It can be lead 2. All right, and if we're lead 2, we would lose that electron and that electron, and we'd be 2+. Alright, but if we also lost the 6s's, we would lose 1, 2, 3, 4, and we could be 4+. So looking at the electron configuration of lead, I can be 2+ or 4+ very, very easily. I'm probably not going to be 3+. I'm probably not going to be 1+. Why? Because why would I just lose one of those p electrons? I'd lose both of them. I'd most likely lose both of those s electrons. And I'm probably not going to use any of the purple, right? Any of the 4f14 or 5d10. Those are very, very stable. Alright. So in the last two here, lutetium. Where's lutetium at? Well, it's way down here. Okay. So we have xenon. And then we're going to have 6s2, 5d1, 4f14. Alright. There we go. And fine, well, we can do the 4f. We'll do it. Why not? 1, 2, 3, 4, 5, 6, 4f. There's 14 of them in here, so that's full. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This guy. So ends 4. L is 3. M sub L, last one is 3. MS down, minus 1/2. And finally, last but not least, uranium. And uranium we get to use radon for. Alright, because uranium is right there. The last one on the planet that exists naturally. Okay, so where do we start? Looks like it's 7s2. Right? 6d1, 5f, 3. So 5f3, 1, 2, 3. This guy. Ends 5, L is 3, negative 3, negative 2, negative 1, and plus 1/2. And that's the electron configuration of all these atoms. Alright, so hopefully that makes sense. Hopefully the patterns are visible, and we'll bring you more of this in the next video.